So I've made this video because I have a number of friends who enjoy gambling, especially at the native casinos where I live in San Diego County, which I think is the county in the United States with the most native casinos. But of these friends that like to gamble, none of them seem to like math at all or understand it much. And I'm thinking that maybe math, and especially probability theory or computing odds, is something that people ought to better understand if they're going to gamble. So that's why I've made this video. Okay, the prerequisites for this, the things I want you to understand coming in so that this all makes sense, is you need to know arithmetic. You need to be able to know how to add numbers and to subtract numbers and to multiply numbers. Now this is where it gets a little weird because when you're young they teach you to use an X for multiplication. Later on they may teach you to use a dot, and then after that they may just say we're going to stick things together like AB is the same as A times B. And then if you learn to program computers, they typically use an asterisk for this. But it's all the same thing, it's all multiplication, you all know how to do that. Pop quiz, what's 7 times 8? If you don't know the answer, this may not be the video for you. Okay, and we're also going to want to deal with division. Sometimes we do this, you know, A divided by B. Sometimes we do it with a big horizontal line. Same thing. And in addition, I'm going to want you to know how to add fractions. There's a couple ways to think about this. One is to just do it with symbols. Another is to use pie slices or pizza slices. So if I've got a pizza and I've cut it into a third and I've got another piece that's a sixth, and I want to add a third and a sixth, well, for one thing, if you look at it right here, you can pretty much tell that it's a half. But let's not be sloppy. So we're going to go 1/6 plus 1/3. If we multiply this by 2/2, and you know, you can always multiply anything by 1, and a number divided by itself is always equal to 1. So we can just say, okay, we're going to take this a third and we're going to make it 2/6 and add 1/6 to it and end up with 3/6, and then you can reduce that to 1/2. So if this all looks like something you know how to do, then this is the right video for you. If you find it too tedious to add fractions, you can always use a calculator. It will compute decimal approximations, but that's probably close enough for what you want. If you really want the exact answers, you can also use a symbolic solver, such as Wolfram Alpha or Mathematica or Octave, that'll actually let you put in the fractions and will give you the fractions out as a result. So that's something you can do if you're in a hurry and you just want to get these calculations done. I also would like you to know how to compute percents. And if you've ever been driving down the road and seen a speed limit sign, in the United States they sometimes say mph for miles per hour. In Europe they'll say kph for kilometers per hour, or k/h for kilometers divided by hours. And the point I'm making here is that that P stands for per. Per means divided by. So when you look at the word percent, it's actually short for the Latin percentum, which means divided by 100. So if you've got some number, like a half, which is 0.5, let's add a 0 to it, it's 0.50, we can say, well, that's 50 hundredths. And then if we just come along and say, well, let's get rid of this divided by 100 and write a percent sign, which means divided by 100. So it's the same thing. So those are pretty much all of the prerequisites. And so now let's get into figuring out how you compute odds, or sometimes called probabilities. Okay, I wanted to quickly tell you where this came from. I always heard a story through most of my life that there was some French mathematician, I forget which one, who was playing whist, which is kind of like bridge, with some friends. And they had a bunch of money on the table, and a messenger came, and one of them had to leave because of an emergency, and they couldn't agree on how to divide up the money on an unfinished game. And so the French mathematician volunteered to study the problem and invented probability theory to answer the question. Great story, but I can't find any evidence on the internet that it ever happened. So I looked at the Wikipedia article for probability theory, and it told me that it was originally started out in the 8th and 13th centuries by some Arabs named Al-Khalil Al-Kindi and Ibn Adlan, followed on by some Europeans in the 16th century, Girolamo Cardano, Pierre de Fermat, Blaise Pascal in the 17th century, Christian Huygens in the 17th century, and Pierre Laplace in the 19th century. So, swell bunch of guys. Thank you all for your hard work in figuring this out, but it just doesn't make as good a story, I'm sorry to say. So really quickly here, I want to get some terminology squared away. I called this talk Figuring Odds for Gamblers. I use the word odds because it's a short word, and I'm trying to make this seem like it's not scary. But odds and probability are actually not exactly the same thing. If someone tells you the odds of something are 3 to 2, what they're telling you is that it's 3 out of 5 and 2 out of 5. In other words, you add these numbers together to get the denominator, and then the numerators are those two other numbers. So that's just a quick conversion from one to the other. In most cases, it doesn't matter much. Like if someone tells you the odds are, 1 to 1,000,000, that's 1 in 1,000,000 plus 1. It's almost the same thing. But anyway, just want to make sure there's no confusion about that. So I want to talk just for a moment about symbols. This is going to be the scary part. So put on the Michael Jackson Thriller music, get your popcorn, and let's talk about symbols. If you get a textbook out of the library on probability theory, they're going to start doing stuff like this. They're going to say, consider an event E, which has a probability P of E. And E is an event that is in a set of events, like E sub 0, E sub 1, E sub 2. And then we're going to say that any given element, like E sub 0, is an element, this little epsilon of the set E. And we may also want to do calculations on numbers like 7 factorial. And you may also find that in more advanced work, they're going to use something called predicate calculus, which will give you these upside down A for all and upside down E for exists. Now, I'm here to tell you that you don't need any of these symbols to figure out odds. The symbols are useful because mathematics is an international language, so if you write this way, people all around the world can understand it. Also, it's the way you go about proving stuff. Well, we're not going to prove anything. You're just going to have to trust me. And this is all in English, so we don't need to worry about people in other countries or in other languages, just fine if you're in Australia. And so we're just going to not bother with the symbols, and I'm sure you're all very relieved about that because I found that a lot of math anxiety has to do with looking at this kind of stuff and going, I don't know what this means. So let's move along. So I want to talk for a second about some of the misconceptions people have about odds. I've heard people talk about the law of averages. Well, I'm here to tell you there is no law of averages. There's something called the law of large numbers, and that says that if you do something with a known probability, like flip a coin, a whole bunch of times, millions of times, it'll work out to be almost exactly 50% heads and tails. All the little variations will even out in the long run. But the law of averages is the belief that people have that if you start out and you get like a bunch of tails, later on you'll get a bunch of heads to even it out. And that's not how it works. It's more like diluting. It's like if you have a glass of water and you add a few drops of blue and it turns blue, and then you add like a swimming pool's worth of plain water to it, the blue's going to disappear, not because you took any blue out, but because it's diluted by the other water. And this is what happens with the law of large numbers, is that the variations you see initially are diluted by the large numbers of events. But there is no evening out because the coin has no memory. It doesn't know what happened before. It approaches every flip as a new random event. And that brings me to another concern I have, that you're going to see clickbait all the time on the internet that says, how to tell if a slot machine is about to hit. Well, let me tell you something. You can't tell. It's random. People have worked really hard to make it random. That means nobody knows. The slot machine doesn't know. The people who built the slot machine don't know. And certainly, you're not going to know. Now, slots began, really, the initial concept was Wheel of Fortune. I'm sure you've all seen these things, or maybe you've seen the game show. And then it occurred to someone at one point to turn the wheel sideways, put in 3 of them, and have a little window where you could see how they line up. And during those early days, when you were putting coins into the slot machine, there was a separate bank for the payout, and some of the coins would go into that bank, and some of the coins would go into a compartment where you're never going to see them again. And so it actually was the case that if you played for a long time, the bank would get bigger and bigger, and so when you got a jackpot, it would be bigger. That doesn't mean the odds got better. It just means that if you did win, you got more quarters. But they don't work that way anymore. You put a card in, an electronic chip generates the random numbers. There's no way you can guess those numbers. And when you win, it just pays out an amount that was determined by the program. And I might as well mention right now that I think slots are a terrible idea for a game because it's really hard now to figure out the odds. Back when we used wheels, you could just count the number of partitions in the wheel, and it was a simple math problem. We'll see that in a few minutes, how to do those calculations to figure out the odds. But nowadays, nobody knows. I've done a lot of research on the internet to try to figure out what the odds are on the slot machines you see in the native casinos. Nobody's saying. They're very unregulated. And as far as I can tell, they only make them pay out good enough to keep people coming back. They just try to find that sweet spot where if they gave you less, you wouldn't come back, but they certainly don't want to give you more. So why play a game you don't understand? I'll mention this again later on, but it's important to understand the games you play if you have any hope at all of winning. Okay, so the first rule, I'm going to call this Rule 0, is really just sort of a mental shortcut, that if you've got a number of events that might happen and you don't see any reason why any of them would be more likely than the others, you typically just assume they all have the same probability. Now, this could come back and bite you later. If you really want to be sure, the way to do it is either to totally analyze the situation or do some experiments and take statistical results and look at them. But like if you're rolling dice, you go into a casino, they hand you the dice, you're going to roll them. You don't have time to check out the dice. You don't have time to do a bunch of tests and see if they're fair. You're just going to have to go with it. So you're like 6 sides, 6 ways it can turn out. I can't see any reason why any of them would be favored. So each of them is going to end up being 1/6 probability. So that's Rule 0. I mentioned it as like a half a rule because it's not very reliable, but people do it every day. Then Rule 1 is that if there's a number of different things that can happen and they each have a probability, if you add up all the things that could happen, all the probabilities have to add to 1, which means the probability of something happening is always 1. Or sometimes we call that 100%. Sometimes this is handy because you can calculate the odds of something not happening more easily than you can of it happening, in which case you figure out the odds of it not happening and you subtract that from 1, and that's the odds of it happening, because everything has to add up to 1. So, for example, if you've got, again, these die, you're going to say the odds of it coming up with 1 dot is 1/6, and it's going to be 1/6 for 2 and 3 and 4 and 5 and 6. 1, 2, 3, 4, 5, 6. And if you add all these up, they're all going to add to 1 because one of those sides has to come up. So rule number 2 is the rule of OR. If you want to know the probability of one thing or another happening, as long as they're mutually exclusive, as long as they can't both happen, so the coin has to either come up heads or tails, but it can't be both, then the probability of both of them happening is each probability added to the next. So you add when it's an OR and it's mutually exclusive. And then the third rule is the rule of AND. If you want to know the probability of one thing and another happening, then the second one has to be dependent on the first. You say, well, the first event happened, and since it happened and we know it happened, we're going to look at the odds of the second event happening. And so the probability there is the first probability of the first event happening times the second event given that the first already happened. So that's the rule of AND, which is that you multiply. So if you flip a coin and you get heads, and you flip it again and you get another heads, The and there is 1/2 times a half, so it's a probability of 1/4 that both of those are going to occur. So I want to talk for a moment about gambling devices. Calculating odds is usually easier with gambling devices than going out into the wild. Like, what are the odds of seeing the first robin of spring on a Monday? You know, that's a tricky question. But the odds of rolling a 6 on a die, 1 in 6, you can be pretty sure of that. And why is that? Because people have been using dice for thousands of years. They wouldn't use them if they weren't fair. They want fair gaming. And whenever they encountered a problem, they made a little tweak until it got better. So if you look at coins, you look at dice. More recently, there's Dungeons and Dragons dice, which I really like because you can do so many things with them. There's picking a card from a deck. You know, it's like if you want an event that has a 1/7 probability, just get the cards ace, 2, 3, 4, 5, 6, 7 and pick one. And there's your 1 in 7 choice. And all of these techniques, like I say, have been honed by thousands of years of use by humans to become fair events. And I want to mention also that when you go to a casino, the chances of them trying to cheat you are very low. And there's 2 reasons for this. Number 1, if they get caught, they can go to jail. Bad things can happen. They can lose their license. And number 2, they don't need it. The odds are so much in their favor that if every game is fair, they're still going to take you to the cleaners. Also, I found this cute spinner on the web. I just searched for interactive web pie chart spinner, and I found this page. You can see the URL here for a teachers association that is useful for classroom use. And as you can see, you can pick the number of slices. They're each a different color, and then you can spin and get a random choice that way. So that's handy if you're in a hurry and you want to be able to specify different odds for different events and just do some random experiments. So for our first example, let's consider a problem that, according to Wikipedia, was one of the things that got probability theory rolling in the first place. The French mathematician Fermat, F-E-R-M-A-T, Fermat they sometimes call it in America, is famous for something called Fermat's last theorem, but we won't get into that. Anyway, he had a friend who wanted to know if he rolled a 6-sided die 4 times, what's the chance that he'll get at least 1 6? Well, this is one of those things that's a little easier to calculate the opposite. So we're going to say, what's the chance that you don't get a 6th? So it's like on your first roll, it's going to be 5 6. If you get a 1, 2, 3, 4, or 5, you didn't get the 6. And then you're going to do it 3 more times, so you're going to go 5 6 times 5 6 times 5 6 times 5 6. And then when you multiply these all out, you get an answer. And because I'm lazy, I'm going to use my iPhone, and I'm going to bring up the Wolfram app, which I believe I paid $3.99 for, worth every penny. And so I'm going to go 5 divided by 6 times. Now I think what a better idea would be to just raise it to a power. So I realize I didn't warn you that this might happen, but for those of you who know what it means to take something to a power, I'm going to take 5 divided by 6 raised to the 4th power, which is just the same thing as multiplying it times itself 4 times. The result is 625 divided by 1,296. So that's about 48%, so it's a little less than half. So if you're betting someone, on even odds that you're going to do this, you're going to be okay, because that 48% is the odds of failing. So your odds of succeeding will be 1 minus 0.48, which is 0.52, 52%. So that's our first example. So for our second example, let's take a famous situation in poker. You're playing draw poker, and you end up with this hand. You can see that you've almost got a straight. You don't have the 3, but you got the ace, 2, 4, and 5. So you might want to say, well, let's just turn in this queen, draw another card, and see if I get the 3. And they call this drawing to an inside straight. It's sometimes called a shotgun for reasons I do not understand. And the question is, what are your odds of getting the card you want? So there's 4 cards in the deck that could give you the straight you want. The 3 of hearts, the 3 of diamonds, the 3 of clubs, and the 3 of spades. And the probability of getting each of them is 1 in 52. So you want to know what are the chances of getting this or this or this or this, and they are mutually exclusive, because if you get one, you're not going to get the others. So you just add them up, and the answer is 4 52s, which is 1/13. So that's your odds on drawing to that inside straight. Now I have to point out, I just did this wrong because you're not drawing from the entire deck. You've already got 5 cards too. So whatever the number of cards have already been dealt, just subtract them from your 52s. And then when you add up, you'll still get 4 in the numerator, but you'll have a smaller number in the denominator. So your odds are going to be a little bit better, but it's still not a very good bet. Okay, now I'm going to teach you a handy tool called a Markov chain. Now, when I was taught these, I think they called them Markov trees. And they look more like trees than chains to me, but the literature now refers to them as chains, so we'll go with that. The idea is you're going to take these relationships between the ands and the ors, and you're going to express them in a branching tree. So you start out with nothing happening, and that's just a black dot. And then we say, okay, there's going to be one event or another one. So we're going to give them each a probability, like maybe this is a coin flip. So this is a 1/2, and this is a 1/2. And that's going to take us to a heads or a tails. And then perhaps what we're going to do next is we're going to do a 3-way spinner. So there's 3 choices, and they're each probability 1/3 of getting us like a red, green, or blue pie slice. And when we go to figure out, and of course this is an and relationship. So 1/2 and 1/3, it's like what are the chances you get a head and a red? You multiply them, 1/2 times 1/3 is 1/6, so 1/6 is what you end up with out here. And likewise, if you want to know the ors, what's the chance of getting head or tail, you add them, and so you end up with 1 being the chance. And if you add up these, all 3, or what's the chances of getting just a red and or a green, it's 1/3, and 1/3 is 2/3 for those 2, and you're leaving out the other third. So this allows you to visually represent these and relationships, these or relationships. And it also helps that because there's this chain being formed, it reminds you that these events out here have to be dependent on the other events happening first. That you can say, what are the odds of getting a red if you got a heads? And likewise, these events that are on the forks are or relationships. They have to be independent. You can't go both ways. You can go one or the other. So that's the basic tool. So let's look at a more complicated example. Let's say that someone proposes a bet. You're going to flip a coin, and you decide that heads equals 1 and tails equals 0. And you're going to keep a cumulative score. If it comes up heads, you're going to roll a 4-sided Dungeons & Dragons dice, which has labels on it 0, 1, 2, or 3. If it comes up tails, you're going to roll a 6-sided regular cube die, which has 1, 2, 3, 4, 5, or 6 on it. And you're going to add the numbers as you go. So the question is, what are the odds of getting 4? And let's look at that. We start out again with nothing happening. And the first thing we do is we figure we're going to flip a coin with half odds each way. And if we get heads, that's worth a 1. Tails is worth a 0. And then for the heads, we're going to roll this 4-sided die, the one that looks like a triangle-based pyramid. And we're going to get 0, 1, 2, or 3 is going to appear on the face on the bottom. Is typically the one you look at because the top is pointy. But anyway, and they're each a 4th. Or if you get tails, then you're going to roll the 6-sided cube die. And each of those is a 1/6 chance, and they're going to be 1, 2, 3, 4, 5, or 6. Now let's look at our outcomes here. If you get the heads, that's a 1, and then you get this 3, that's 1 plus 3, that's a 4. And the probability is 1/2 times a fourth, which is 1/8. If you go the other way and you get the tails, you've picked up a 0 so far, and then you get a 4 from the die, that's got a probability of 1/6. So here's your other 4, which is a 1/2 times a 6th, which is a 12th. Now these two, you want to know the probability of one or the other happening, so that's an add. So you just have to be able to figure out what's 1/8 plus 1/12. And I should mention that when you're trying to find a number that makes a common denominator, the mathematicians will tell you you're looking for the least common denominator. But the fact is, it doesn't matter if you get a bigger one. You're still going to get the right answer. So we look at this and we go, okay, we can multiply the top and the bottom by 3, and we get 3/24. We can multiply the top and the bottom of this times 2, and we get 2/24. We end up with 5/24, which is a little bit bigger than 20%, maybe 22%, I'm guessing. Our calculator would be happy to tell us. So that's your chance of getting a 4. So that shows an example of how to use these rules for and for or while drawing the chain. And this is the way that you can figure odds for just about anything in math. The only time it gets complicated beyond this is when you deal with picking problems, like in a Keno game. And I'm going to go into that in another video, but let me just mention that I did some calculations earlier today. And from what I can tell, if you played Keno every 5 minutes, until you reach the point where you had about a 50% chance of winning a 15-spot bet, which is the most spots you can bet in some parlors, it would take you about 2.8 million years at a game every 5 minutes to get to the 50% point of winning. And by that time, you will have spent many tens of millions of dollars to try to win a $10,000 jackpot. So I'll look forward to in a future video, I'll show you how to compute that. But if you're not dealing with picking, if you're just dealing with situations where you have ands and ors, this is all you need to know to compute probabilities. So when you're deciding whether or not you're going to take a bet, there's 2 things you need to consider. The first is, what is the expected value? And the way you compute expected value is just for each possible outcome, you take the probability and you multiply times the money you're going to make or lose. And then you just add all these up. You've got, like, if you're flipping a coin and someone says they'll give you $5 if it's head, but you lose $6 when it's tails, you're going to go, okay, that's a 1/2 times $5 plus a 1/2 minus a 1/2 minus $6. Or I'm sorry, let's call it minus 1/2 times $6. You're losing $6. Okay, a 1/2 times minus $6. That's my final offer. So you add these up, and this is 250 minus 3, so you're losing 50 cents. It is your expected value is a loss of 50 cents on every toss. And when you look at that, you go, okay, well, gee, if I could play this game 1,000,000 times, you know, I'd lose $600,000 on average. So that allows you to calculate the expected value of any run of games. But there's this one other thing you have to consider, which is your tolerance for risk. And the way that'll manifest is that you may have an opportunity, like what if I told you that if you give me $1 and then I spin a wheel of fortune that has 1,000,000 entries, and if it comes up the red star, 1 in 1,000,000, then I'm going to give you $2 million. Well, that's a great expected value, but the fact is you could probably play for months and never see any money at all. So the real question is, how much are you willing to lose on the way to winning? And you know, how much of a bummer is it for you to have this drain on your finances that may not, you know, there may be a generation before anyone in your family gets the money. So that's what I call that risk tolerance, because it has a factor in it that has nothing to do with expected value, which is what's it going to be like for you on the journey, not just what's the final result. So you always want to think about that as well. Okay, I want to talk for a moment about gambling strategies.
My general opinion is that most strategies are worthless. People come up with these ridiculous ideas and manage to convince themselves they're going to work, but they don't. But one of the most famous ones, and one that I just wanted to focus on because it's so seductive, is what's called the martingale strategy, and which I call losing the farm. And the way this works is you play an even game like red or black on roulette, although I want to point out that that's not an even game. The green 0 and double 0 are going to drop your odds down. But ignoring that for a moment, you bet 1 unit, let's say $1 on black. And if you win, put that in your winning bag. If you lose, you double down, $2. If you lose again, you double down, $4, $8. Keep doing that till you win, and that wipes out your losses for that sequence, and you go back to betting 1. So every now and then you're going to get another $1 into your winning bag, and you're not going to lose anything. However, there's 2 big problems with this. The first is that most casinos aren't going to let you give huge bets, and these bets get huge very quickly. If you end up losing 10 in a row, you're betting 1,024, or more than 1,000. If you lose 20 in a row, you're betting 1,000,000. So you have to have, that's the other problem, is you have to have the money. And you're putting at risk everything you own. You have to be like Elon Musk, betting millions or maybe billions of dollars, and each time it's to win $1. Well, there's a great little video that I'm going to put the URL up for you here, that where someone analyzes this and says that if you start out with $1 million and you play the martingale strategy until you either double your money or you lose all your money, your chance of doubling your money is 1 over the mathematical constant E. You can look on Wikipedia to find out what that is, but that gives you about a 36% chance of doubling your money, and the other, 66% is that you're going to lose it all. And he said if that's what you're playing for, and it's going to take you a very long time, millions of roulette spins to get this outcome, you're better off just putting the entire $1 million on black, because then your odds go up from 36% to 50%, and it's all over in 1 spin. So something to consider. And if you're actually thinking about using a strategy, you'll want to keep in mind my next tip. So you should never go in and risk real money unless it's a tiny amount, unless you're just having fun. But if you're actually trying to win money gambling with a strategy, you should never go in with real money until you've simulated the strategy. And there's basically 3 ways to do this. There's manual, semi-automatic, and automatic. And manual means you just play the game, either by yourself or you get a friend to play with you, and just use the strategy you would use, play with pennies, figure out whether you're winning or losing. And if you can't win at home with your friend there, with open book test, access to your notes, and no dealers or supervisors looking over your shoulder, no hidden cameras. If you can't win in that situation, you got no chance in the casino. The second approach is semi-automatic, where you either find a game you can play on a computer or on a web page, or else you program one. I realize most of you probably don't write programs, but if you can learn a simple programming language. When I was younger, BASIC was all the rage, and you can still get a hold of something called Visual Basic from Microsoft. And then a language that's up and coming is called Python, which is named after Monty Python, which I think is hilarious. And although it isn't a simple language, you can use it in simple ways. And if you learn just enough to be able to do some arithmetic and take input, add, subtract, multiply, divide, you can use that to create a little casino simulator, and then you play against it. Or maybe you have a friend who programs and they can write you a simulator. But either way, you make the decisions on what to gamble, and then the computer tells you whether you won or lost. That's the semi-automatic approach. The fully automatic approach is to simulate the casino and the player. And the advantage of doing this is then you can play like millions of games, billions of games, and see under the law of large numbers what the outcome is going to be for those games. And that's really the best way to stress test a strategy, is to fully simulate it like that. But in any case, you need to know going in that it's going to work, because people come up with the most wacky things and they sound good, but they may not really work. So I want to talk about how to win. First of all, you need to know that most of the games in the casinos, you can't win. But there are a couple. There's blackjack, also called 21, there's craps, and there's poker. With blackjack, what you really need to do is count cards. Now, they would love to make this illegal, but they can't because it involves stuff going on in your head. How do they know? But if it looks like you're counting cards, if you're winning the way people win when they count cards, you're betting the way people bet when they count cards, they can throw you out. They can throw you out for any reason. Probably except like, the protected categories, like they can't throw you out for national origin or something. But anything they think is wonky about your behavior in the casino, they can eject you, they can ban you, and they don't need to say why. So that's the toughest part of counting cards, is not keeping count, although that is kind of tricky. It's looking like you're not doing it. Second of all, there's craps, which I have only studied this briefly, but I'm told that sometimes in crap games you reach a point where you actually have a slight odds advantage, and that's when you want to bet large. And so if that's something of interest to you, look into that, see what you can do. Thirdly, poker is useful because you're not playing against the house, you're playing against all the other players, and so the house is just taking a cut. So if you can beat the other players by enough, you can win. But of course, this is a game that combines odds with psychology. You not only have to know the odds on the cards, you have to be able to figure out what's going on in the heads of the other players. And that's really tricky. That's like one of the hardest things that humans attempt to do, is to understand other humans. But those are ways to win. And lastly, I'll say, if you just play some silly game like, roulette or slots, heaven forbid, the key to winning in that environment is to quit early. If you happen to win a jackpot, or you happen to get a large payout, stop, because it isn't going to happen again soon. And I've had some experience with this. Maybe sometime I'll tell the story about how I won about $30 in roulette, turned it into quarters, and was using them in the vending machine at work for the next 6 months. And every time I bought something, I felt like a winner. Now, if you really want to play with the big boys and girls when it comes to gambling, you should investigate the Chicago Board of Trade, where you can go in and win or lose millions of dollars betting on things like the future of corn prices. And another approach is to buy casino stock. Since the odds are against you every time you gamble in the casino, the people that own casino stock are getting the advantage of those odds. So in conclusion, I want to encourage you, unless you're just playing around with tiny amounts of money you can afford to lose and it doesn't matter, that you should never gamble in a game you don't understand. And the whole point of this probability theory tutorial here is to help you understand how to calculate the odds. But let me close with a quote from the musical Guys and Dolls, which, as you may or may not know, is about gangsters who like to gamble. And the main character explains this to a comrade of his. My father once told me, one of these days in your travels, a guy is going to show you a brand new deck of cards on which the seal is not yet broken. Then this guy is going to offer to bet you that he can make the Jack of Spades jump out of this brand new deck of cards and squirt cider in your ear. But son, do not accept this bet, because as sure as you are standing here, you're going to wind up with an ear full of cider.